Good morning, ladies and gentlemen, at least this morning for me. So we're going to continue talking about light in our effort to get closer to what light and electrons have in common. So today we're going to talk about two of these three things that you see here. We're going to be talking about blackbody radiation, and we're going to be talking about the photoelectric effect. So classical physics, so these are three phenomena that could not be explained by classical physics. So blackbody radiation, let's just talk about what that is. Blackbody radiation is when really, really hot things give off light after being heated. So a great example of this is if you look in your oven when the coil heats up. If you have a coil electric oven, you can see that metal substance, that when it's heating up, it actually turns a color. Now you can see in the bottom left picture here, I have a coil, and you can see that as we get closer to the tip, it's getting lighter and lighter. So the lighter the color, the hotter that part of the object. So this is called blackbody radiation. Could not be explained by classical physics. Why is this thing giving off light when it's heated? What kind of implication does that have? The second thing that we're going to talk about is the photoelectric effect. The photoelectric effect is when light of a certain minimum frequency hits the surface of a metal, it ejects an electron. Not just any light, but light of a certain frequency or above that frequency will eject electrons from the surface of the metal. Now this is actually an application of this is actually in photography, at least the old types of cameras that were around, where you had actually an actual film roll that you had to change, or even the what's it called? The instant, I forget what, Polaroids, or even Polaroid cameras. I use this concept, bringing that light in, strikes the surface of the metal based off of the color of the light coming in, and that would actually eject those electrons, forming an image on that film. So the photoelectric effect is an application of photography before we had digital cameras. So the emission spectrum, I'll go ahead and explain a little bit about this too. The emission spectrum is when it's unique for each element. Elements have a unique emission spectrum that are like its fingerprint. So you can see here I have 4 different examples, and I couldn't tell you which element is each one of these, but when an element is excited, it gives off light. It can give off light, and when it gives off light, it usually gives off a particular color. And if we take this and we run it through a prism or something to refract the light, we will get a breakdown of the different wavelengths of light that are composed of that one color of light that we see. And that is an emission spectrum. Classical physics could not explain these 3 phenomena. So we're going to get into more detail with blackbody radiation and the photoelectric effect. All right. So Max Planck, he actually explained how radiation is emitted by hot objects, or this concept of blackbody radiation. So he assumed that the energy is going to be released or absorbed in discrete quantities, and he called these quantities quantum, or for plural, quanta. And again, a quantum is a discrete chunk of energy, a fixed amount, a very specific amount of energy that is being given off. So it wasn't just that there was just a release of energy. It was that there was a release of energy in these certain amounts, not just any amount, but certain amounts, and not continuous. So he actually found the relationship between the energy that's being given off to always have this relationship here with Planck's constant. So the energy divided by the frequency would always give the same number, which we call Planck's constant. So you could have 1h nu, or 2h nu, or 3h nu, but you couldn't have anything between that. It's kind of like walking up steps. When we walk up steps, we can't take 1.5 steps or 2 3/4 of a step. You either take 1 step, 2 steps, 3 steps, and if you're really, really good, you could maybe take 4 steps. But it was always in these in multiples of h nu. Now he really couldn't explain why, but it worked. And so in walks Albert Einstein in an attempt to explain the photoelectric effect. Why does light with a certain minimum frequency cause electrons to be ejected, but if we're below that frequency, nothing happens? So here's just an example for potassium. We see that red light hits it, which has a long wavelength. If you think back, red light has a long wavelength, which means it has a low frequency. Then we have this green light here hitting it, and we see that an electron is ejected. Red light, nothing happens. Green light, ejected. Has a wavelength of 550 nanometers. We could take this and calculate the frequency. And we see it also happens with blue light. Now you may also see that the velocity of the electron starts to increase as we increase the frequency. That's because of it takes a certain amount of energy to eject the electron, but any energy that's left over from that light will go into the speed of the electron, the kinetic energy for that electron, and so it'll be able to move faster with higher and higher frequencies above that threshold frequency. So to explain this, Albert Einstein took Planck's theory a step further and said not only is it a discrete chunk of energy, not only does that light exist in a discrete chunk of energy, but it actually is a particle of energy, which he called photons. So packets of energy that behave like particles. So basically particles of light. And he basically said, if a photon has enough energy, when it strikes the surface of the metal, then it'll eject an electron. Boom. And so we can think about this using Planck's constant. We can think about this using Planck's constant. The energy of a photon is going to be equal to that energy of the quantum, which again is equal to h, the product of h nu. Where h is Planck's constant and nu is the frequency. So basically, what Albert Einstein was suggesting here is that radiant energy itself is quantized and actually behaves like particles. The photoelectric effect is a great example of that. So, and again, it's important to know that each metal has a different threshold frequency. Here we see that threshold frequency is somewhere between 700 nanometers and 550 nanometers. Now you might be thinking you just said frequency, but you're talking about a wavelength. Remember, they're inversely proportional, and so with 550 we're talking about a higher frequency than with 700, and so it'd be some color of light between this. And how do we know this? Because green light here, there's some amount of kinetic energy that the electron has, so I'm assuming that the frequency would actually be something just a little bit lower in frequency than what this green light has right here. All right, so this brings us to a very important question. Is light composed of waves or particles? What do you think? To be discussed in class. But I will say, do not think about it as a wave of particles. That is the wrong idea. But is it composed of waves or particles? And I'll leave you there. Have a great time studying chemistry. Well, we're in some physics right now, but I hope it's been informative, and have a great day.